fundamental forces. So they saw that if you go to certain very extreme scales, very tiny scales, or very hot temperatures, or very high energies, you can actually unify the non-gravitational forces. So you can unify electromagnetism with weak nuclear force and strong nuclear force. But even then, that still doesn't unify all those three with gravitation. So we still have this question of what's the more general answer and explanation of all of these things, and that's where we're trying to find a better theory, or a more grander theory, or a broader theory. And string theory or superstring theory is basically a grand unified theory candidate. Okay, so that's the point of string theory. That's why people worked on it. That's what they're going for. That's what they're trying for. Now, how much they succeed is a different matter. String theory, even though it's successful to a large extent as a theory, it's strong, but at the same time, one big flaw is that we cannot test it experimentally because of all these extra dimensions that it claims to have, that it basically convinces us of having, of being the reality. But because we experience only the 4 dimensions, including time and space, we cannot easily test out string theory and be like, yeah, this is definitely true. So without the experimental testing, it remains sort of a candidate theory and not a testable one. Okay? Geometries, symmetries, dimensions. Hello, Hawkwave Media. So, see you next time, Stephen. Thank you so much for the book. So, that's kind of what's going on. Trying to unify all the parts of physics is not a joke. It's not a trivial goal. Einstein worked on it and didn't quite get there. And in the 1960s, string theory kind of revived itself and brought back this notion of, well, maybe there are extra dimensions, and that kind of makes all the math work out and whatnot. Have you already talked about loop quantum gravity theory? No, we're just talking about the early days of string theory at this point. Have you already talked about loop quantum gravity theory? No, I have not. Whatever that is. It's not really come up yet in terms of, maybe I just don't know exactly what you mean, but it hasn't come up in this discussion so far. So, okay, any other questions about what string theory is trying to do, and anything else before we get started with Kaluza and Klein? So the importance of Kaluza and Klein's work is that, first of all, they were the first people. Actually, it was, I believe it was Kaluza who for the first time gave it a shot. He took general relativity and introduced more dimensions and proposed this interesting sort of unconventional solution, which is that maybe there are more dimensions, right? And so this is sort of the father of string theory, right? And I mean, in a sense, general relativity is a father to string theory, because general relativity also kind of breaks away from the conventional way of doing things, because conventionally we do geometry kind of differently. We do the Euclidean geometry, we have the XYZ. We don't do things in 4 space-time usually. So by making the math kind of different in GR, the geometry was already kind of different and unique. So taking that and adding even more dimensions is something that Kaluza proposed, and it was considered to be very interesting. But it did not necessarily continue at that point in 1919, and it did not get revived back as a full-blown theory until the 1960s. But let's read about what Kaluza and Klein had to do in the early 1900s, okay? The suggestion that our universe might have more than 3 spatial dimensions may well sound fatuous, bizarre, or mystical. In reality, though, it is concrete and thoroughly plausible. To see this, it's easiest to shift our sights temporarily from the whole universe and think about a more familiar object, such as a long, thin garden hose. So this is the